here we have a situation where we're looking at an arm in static equilibrium. And so the question asks, what's the force of that the bicep muscle has to exert to the forearm, and then what kind of force does the elbow joint experience? And so we're going to first set up our forces and then go from there. So we've got the weight of the 5 kilogram mass, the weight of the forearm, and then we've got the forces up from the muscle and also the elbow joint. So if I look at this, I've got the M of the ball times G is down. I've got something right in here. It says the center of mass, that this mass of the arm times G, where mass of the arm is equal to 3 kilograms. The mass of the ball is a 5 kilogram ball. And that is a disc centimeter. This is 15 centimeters, whereas the ball itself is 35 centimeters. I made it so you can't really see that, but mg there. And then the muscle must point up. And so the first thing, you can do a tilted axis here, but the first thing to notice is that we've got 2 downward forces and an upward force. And then over here from the elbow joint, in this situation, we're going to probably have an upward force, but it's hard to tell whether it'll be up or down. But it doesn't have to have any components in the horizontal direction, because we only have up and down forces in this sort of simplified picture. So this would be force of the elbow. This is going to be force of the muscle. And so we can certainly say, using some of the forces in the y direction, adding them all up, these must be equal to 0 for this to balance out. And so that tells me I have force of elbow, probably up, plus force of muscle, and minus MAG minus M of the ball G is equal to 0. That's our first equilibrium condition, matching all the forces. And then notice we don't have to worry about any X forces in this setup. Now, the thing to notice is that both of these are unknown, so this doesn't get us very far. And so our second equilibrium condition is adding up all the torques so that those go to 0. And the torques are going to be a little trickier, right? Because if we look at this, we have, and we're going to do the torque about the elbow because that's the hinge. So, and the thing that's nice about that is then there's no torque from the elbow itself, okay? There's just this torque applied by the muscle. So if we look at the torque by the muscle, for example, so let's draw that in. Here's the force muscle is up, and then the radius is like this, right? From that, that's only 4 centimeters, right here, that distance. And we know that we've got a 60 degrees right there, because that's the angle of 60 degrees. So the torque from the muscle looks like, of the muscle times R, 0.04 meters, times of 60 degrees. And that's a torque that rotates, right, this torquation, okay, which we might call the positive direction. The other two forces, the weight of the arm and the weight, are going to be causing a rotation in the other direction. Looking at the screen, that would be in a clockwise direction for the other torques. And so if we look at this, then for the arm, so let's do the arm next, like MAG, and then we've 15 centimeters around angle. So this is 60 degrees, which makes this 120 degrees right here. Arm, MAG, the force, times the moment arm, the radius, 0.15 meters, I've already converted that, times sine of 120 degrees. And we've got the same thing happening for the ball. the ball would be mass of the ball times g. This time it's a different radius. It would be 35 centimeters, 0.35 meters right here, of 120 degrees. Now the thing about this is that sine of 60 and sine of 120 degrees is the same thing. This is 0.866, 0.866, 0.866. So we don't really need to include them. I mean, we can define the value of the torque, but we don't actually need them in our equation because we're going to put these into the equation where the sum of the torques equaling 0 is going to be the torque of the muscle minus the magnitude torque A minus torque of B is equal to 0. And putting everything in here, I'm going to have force muscle 0.04 sine of 60 degrees minus MAG times 0.15 sine of 120 degrees, and then I'm going to just put this equation in, minus m, mass of the ball, g, times 0.35 meters, times sine of 120 is equal to 0, and so all of these are equal to the same thing. I'm just going to divide them out to make my life easier. And so I'm going to have force of the muscle times 0.04 meters. So that's meters. This is meters. Is equal to then, taking both of these to the other side, is equal to MA. Let's go ahead and put those values in now. MA is 3, so it's going to be 3 kilograms times 9.8 meters per second squared times 0.15 meters plus mass of the ball 5 kilograms times 9.8 meters per second squared times 0.35 meters. And so then I just multiply things out. This one is equal to 4.41, it looks like, and this one is equal to, and that would be Newton, let's do this. This is 17.15 Newton meters, because this and this is a Newton times a meter, and so this would be Newton meters. And so then adding those together, right, and dividing by the 0.4 gives us our muscle force of 539 newtons. It's a really big force, and you could be worried about, wow, that's a big number given that I've only got 4 Newton meters and 17 Newton meters. But the issue is that this muscle is pulling up really close to the point of rotation. So it really has to provide a big force to counteract this force, the smaller force that's out here, 5 times 9.8, which is 49, but it's much further out. And so this has to be a fairly big number. Once we have that number, it's fairly simple to plug all of these things in, plug this number right in here to find the elbow force. So force elbow plus 539 newtons. And this is where we find out if the elbow force is up or down. And then minus our mg, so that would be 3 times 3 kilograms times our 9.8 meters per second squared, minus our 5 kilograms times 9.8 meters per second squared is all equal to 0. When we solve that out, we do find that the elbow force is indeed up, and I get that to be 461 newtons. Okay, so the muscle needs to provide this, but the elbow's got a good deal of force on it as well in this situation to help support the weight. Okay, so this we found from doing the torque, and this we found from setting up the equation for the balancing the forces. And it's not obvious which one you start with first. You just write down what you know, and then you go from there. The last question, part C, is how do these forces depend on angle? Because the angle cancels out, so this is part B right here. This is part A. And notice since the angle, part C, since the sine of 60 degrees, or 120, is in all the torque equations, and the angle doesn't show up in the other equation, this turns out to be independent of angle. If the muscle didn't pull straight up, if it pulled at an angle, for example, then it would depend on the angle that everything was working. But in this case, at least in our simplified model, it doesn't depend on the angle.